Seth and Jay wrote the following explanations of why the two triangles are congruent. And you can see here we have two triangles, triangle ABC, which is a right triangle, and one side is 4 inches and one side is 5 inches. And then triangle EFD over here is also a right triangle with one side of 4 inches and one side of 5 inches. So you can see they have some similarities. Seth says there are two pairs of congruent sides. Segment AB is congruent to segment DE, and segment AC is congruent to segment DF, which is correct, and a pair of congruent right angles, which is correct. So he says that triangle ABC is congruent to triangle DEF by SSA, which we're assuming means side-side angle. And you can see that since he's put the angle not between the two S's, he's not saying that that's an included angle, but it would be like a non-included angle, which does seem to match what we have going on here. Two pairs of congruent sides and then an angle that's not the included angle between them, but is non-included. Now, Jay gave a slightly different explanation. So the lengths of segments BC and EF are 3 inches, since these are 3, 4, 5 right triangles. So essentially what he's doing is he's using the Pythagorean theorem. He's saying, all right, since they're right triangles, then a squared plus b squared equals c squared. And in both triangles, the c, or the hypotenuse, is going to be 5. So we put a 5 there. And then a squared would be 4 in both triangles, and b squared would be an unknown. So if we solve this, we'll have 16 equals b squared, or sorry, 16 plus b squared equals 25. And then when I subtract 16 from both sides, b squared equals 9. So b is the square root of 9, which is 3. And that's where he comes up with saying that this side would be 3 inches and this side would be 3. And then we would have 3 pairs of congruent sides. Segment AB is congruent to segment DE. They're both 5 inches. Segment AC is congruent to segment DF. They're both 4 inches. And segment BC is congruent to segment EF because they're both 3 inches long. So the triangles are congruent by side, side, side. So who's correct? Is Seth correct, or is Jay correct, or are they both correct? And I'm going to go ahead and say that Jay is definitely correct. I follow everything that Jay is talking about here. He kind of determined using the Pythagorean theorem that the third pair of sides are congruent. So we definitely do have side, side, side congruence there. So I'm going to come down here and I'm going to say Jay is correct in using side, side, side to prove the triangle is congruent. So now the question is, what about Seth? Well, the problem is this SSA is not one of the ways that we learned to prove triangles congruent. What we learned was we started off learning SSS, which Jay used, and then we also learned SAS. Then we learned ASA, and we said, well, if ASA works, then so does AAS. We don't have an SSA congruence. So Seth is not correct because SSA is not a theorem. So that's going to lead us to another question that says, when any two pairs of corresponding sides are congruent, can you show that two right triangles are congruent, and explain? So, that question above, we had right triangles with two sides congruent. Does it matter which two sides that we have? Jay used the Pythagorean theorem to find a missing side that was a leg. But what if we have this situation here, where triangle ABC and triangle DEF are the two triangles we're looking at? And in this situation, we don't have the actual numbers, so we might not be able to do a Pythagorean theorem calculation to find the third sides. But do we need it? I don't think we do, right? Because these two legs being congruent to these two legs, and then the fact that they're both right triangles means they have an angle that's congruent. Well, this would be SAS congruence, right? So triangle ABC would be congruent to triangle, ABC would be DEF. In the top triangles, top pair, because of side angle side. Or in other words, we can say if legs are congruent, then SAS will apply. That's kind of a short version of what we see happening in here. If the legs of one right triangle are congruent to the legs of another right triangle, then we're going to have SAS. But then in this situation, this bottom part, we can see it's more like what we looked at up here, where we have one leg congruent to one leg, and then hypotenuse congruent to hypotenuse. And this is the situation where the third pair of sides would have to be congruent because of what J did up there with the Pythagorean theorem. So if a leg and the hypotenuse, if a leg and the hypotenuse are congruent, then the Pythagorean theorem could be used to prove the other legs congruent. Again, this is just exactly what Jay did in his explanation up there. The other legs congruent, giving us side-side-side congruence. Or I guess it could also be side angle side again, because then we would have what we have here, that the legs are congruent, and then we have the right triangles between those legs. So to answer the question, when any two pairs of corresponding sides are congruent, can you show that two right triangles are congruent? I think our answer is yes. Because again, what we just wrote down here kind of takes us through the possibilities for what those two legs could be. Maybe are those two sides. Maybe they're the two legs. That gives us SAS. Maybe it's one leg in the hypotenuse, one leg in the hypotenuse. So that would give us this other version of congruence. Well, this other version of congruence is what kind of the concentration of this notes sheet in this video is going to be all about. Just take a look here real quick at theorem 4-8. It's called the hypotenuse leg theorem. And it says that if the hypotenuse and one leg of a right triangle are congruent to the hypotenuse and one leg of another right triangle, then the triangles are going to be congruent. So we see over here in this picture that we have two right triangles here and here, right angles there and there. The hypotenuses are congruent. That would be segment MN and segment PQ. And then each of the triangles has a leg that's congruent to the leg on the other. So segment ML is congruent to segment PR. That would indicate by what we call HL, which stands for hypotenuse leg, that triangle MLN has to be congruent to triangle PRQ by the HL theorem. So that now takes us to 5 different ways that we can prove triangles congruent. We have SSS, where two triangles will be congruent if all the pairs of sides are congruent. We have SAS, where two triangles are congruent if they have two pairs of sides and then the included angle between them congruent. We have ASA, where two triangles will be congruent if they have two pairs of angles and the included side congruent. We have angle side, which is where if they have two pairs of angles and then a non-included side congruent. And then finally we now have HL, but HL only works for right triangles. So keep that in mind. HL only works for right triangles. It's kind of implied by the name because right triangles are the only ones that have a hypotenuse, right? So the fact that it's called hypotenuse leg or HL kind of indicates that it only works for right triangles, but I just wanted to give you a little reminder there. So those are now the 5 different ways that we can use to prove that two triangles are congruent.